Ladies and gentlemen, I'm actually very much impressed about the large audience, and I'm very glad to see that the topic of this lecture series, Sensor Data Fusion and Information Fusion, has attracted so much interest. In these two talks I will give before lunch and after lunch, I would like to provide you with some introduction into the methodological background, and primarily I would like to give you a large bunch of examples that may help you to understand the theoretical aspects that are given by Roy Stride, Peter Willis, Stefano Coralucci in the following section perhaps much better. These two lectures addressed in the first lecture this morning the defense domain, and in the afternoon I would also like to address upcoming applications in the civilian domain, in border control, and other aspects. So, in the defense domain, I would like to give you an overview of multiple hypothesis tracking, and I would like to make it intuitive for you to see why this is such an important methodology. Then I would like to address the aspect of sensor management. This was a special example taken from a phased array radar. Sensor management is a very important thing in some sense here. We combine estimation techniques with control theory. And finally, I would like to look at a more advanced tracking application, the production of ground pictures, wide area ground pictures, and the fusion of context information. Before I actually start, I would like to give you a brief overview of where I am from. I am with an institute from the Fraunhofer Society in Germany, and in English it's perhaps a good idea to call us in this way, Institute for Network-Enabled Capabilities. That's our goal. All aspects that are related to network-enabled cooperation are covered by us. We have 4 departments. I'm head of the Sensor Data Information Fusion department. You will see this much clearer. We have, of course, communication systems, information technologies for command and control systems, and the human factors department. We are closely interrelated with the 2 universities, the Bonn University and the Technical University of Aachen. We are essentially a non-profit consultant to the German Ministry of Defense. Our goal is to applied research, and we aim at proof of concept. That means we are doing theoretical work, simulation work, but all this aims at experimental systems or performing large nature experiments to show what it is good for. This is a bridge to the industrial applications and the generation of products. Very important for us is international cooperation within NATO or bilateral. This is an important thing, and I'm very open to start any bilateral cooperation with Turkey as well. Actually, I'm already cooperating with the Turkish border control people. We do have research and development projects with defense industry partner, and our motto is the same motto as the motto of NATO RTO, the sponsor of this event: trusted, unbiased, and competent. So what is it all about? What is the goal of sensor data information fusion? Well, we wish to provide the basis for decisions. Good decisions made by human beings, or by decision-making machines, such as weapon control systems, for example. And this information is harvested from large streams of data coming in. We have sensor data that stream in a large volume, but we have also context information that is stored in databases and is available and can be exploited. And the bridge between the data flood on the other side and the crisp information, the basis for decision support, is provided by situation pictures. That's the key notion. And a situation picture is actually a mapping of a dynamically evolving scenario in the real world onto the computer. As soon as it is on the computer, we can do with it what we want. The task of sensor data fusion in this context is to provide the brickstones, so to say, or the informational elements to build up situation pictures. That means to ask questions like, are there any objects of interest at all? How many are there? Where are they? How do they behave? Can we classify them? Can we even identify them? More and more important is the inference of target interrelations what have the objects to do with each other. Communications, interrelations are very important. If you have an enemy who is doing network-enabled operations himself, he is transmitting radiation, that means he can be localized, he can be tracked, and if the communication people look at what is transmitted, what is communicated, they can infer a lot about the topology of the underlying network. That means the enemy's network-enabled capability is a target for reconnaissance. It may be our own network-enabled capability is some sort of an Achilles heel, because the enemy can do the same, so we are doing the same. Here, I would like to distinguish homogeneous and heterogeneous sensors. Homogeneous sensors are, for example, your two eyes, or a chain of radar sensors. Heterogeneous are perhaps your nose and your eye, or camera sensors and chemical sensors. We can distinguish active and passive sensors. Active radar is well known to you. We have here heard from Matthias Weiss. There's also passive radar, which does not actively emit radiation. Emitter localization is another example for passive radar. Very important are multifunctional sensors. Modern sensor systems operate in different operational modes, and this means that modern sensors have to be managed, have to be controlled. Also, in terms of context information, we can make some basic distinctions. It's very important to model background knowledge. Background knowledge on how the sensors behave, background knowledge on how the targets behave. This is very important. We will see how to get this into the data fusion algorithms. We have to take into account environmental information, for example, travel maps, or if we know that we are looking for targets that move on roads, we have to exploit road maps. And there's also a vast variety of soft information, for example, information on how your enemy is likely to behave, tactical information. Sometimes you have planning information for our own troops. We know where our troops should be, and this we can use to provide better blue force tracking algorithms, and to find out when a plan is actually broken and no longer kept. And we have human reports, human information that has to be taken into account. Information fusion is an important and scientifically highly interesting topic, because the information to be fused is not perfect. It is imprecise, incomplete, ambiguous, it is unresolved, false, deceptive, hostile, in a hostile environment. It is hard to be formalized and even contradictory. So it's an interesting and most challenging research task, actually. It's a broad field, and I would like, a broad field. I would like to show this slide. This slide shows you the first scientific systematization of information fusion. Well, it was done in George Orwell's very year, 1984, so that's quite an interesting coincidence, actually. It is the joint directors of laboratories data fusion model, and here we see that there are several levels of information fusion, levels that are very close to the sensor, levels that are essentially tracking or so. We have situation refinement. Here we take into account the interrelation between individual objects. Impact assessment means to control what we have actually achieved. And level 4 is process refinement, and this is related to the management of information sources. This is a very broad field, actually. But science is not a broad thing. If you do science, you, in a way, drill holes. You have a clear research question, and then you drill a hole until you reach the hard rock bottom of the fact, so to say. And to give you just an idea, here in Germany, in my department, these are the drilling holes, so to say, that we are using. We have a research group, data fusion for array sensors. This is related somehow to the lower levels of information fusion. We have localization and navigation, wide area surveillance, and threat recognition. And during my lecture, I will actually take examples from our ongoing work in these departments. Actually, we have about 50 to 60 persons working there. Very important for us is our link to to the university. This is possible in Germany. I hold a habilitation degree. This means that I can act like a university professor and supervise PhD work. And so we have a mirror of our department at the university. We provide a lecture series, a seminar, and a practicum. It's very important for us to draw young people, young talents directly from the lecture hall into our department. So let's go to to the technical topics. Multiple hypothesis tracking. Most of you have heard this. Why is it so important? Why is it the key technology in many applications? Well, multiple hypothesis tracking is a means actually to deal with problem inherent uncertainties and ambiguities. It's a processing scheme which allows us to do soft or delayed decisions where strict and hard decisions are not possible or are not appropriate. You can say perhaps that the BAYESian approach, the statistical approach, is means to deal with imprecise information in a mathematically precise manner. That's the trick of statistics, the precise treatment of imprecise information. And as soon as we are able to formulate imprecision mathematically, we can tell the computer what to do. Ambiguity is related to the sensor performance, to the environment, the target characteristics, background knowledge. We will see many examples of this in the future, in the next time we are together. Before I'm doing so, however, I would like to provide you a more intuitive picture of what we are actually doing in target tracking and how this description of imprecise knowledge in a mathematical manner is done. The key is that we look at functions of the quantities that are interesting to us. We call everything that is interesting for us as an object a state. The state collects all quantities that are relevant. For example, the position, the velocity, and the acceleration of an aircraft is an example of a state. This state is unknown to us. We wish to infer knowledge about the state as much as possible. And we do this by considering functions of this state. And in this case, these functions are called probability density functions, and this hat-like structure is can intuitively be interpreted. Well, the tip of the hat is we have good hope to find the target there, and as broad, the width of the hat is an indication of the precision of this knowledge. A very broad hat represents poor knowledge. There are other functions depending on the target state. You will see them in the course of the lectures. The intensity function, for example, Roy Streit will talk about this, or the PHD, the probability hypothesis density. Peter Willett will talk about this. All this is the same idea. Consider a function of the quantity that is interesting for us, and this function contains everything you can know about the target. Tracking is typically a process in which time plays a dominant role. Time goes by, the object moves, and so it's very important for us to be able to predict our knowledge. We have present knowledge now, and we wish to predict this knowledge in the future. Here another piece of uncertainty comes into play. We do not exactly know how the target behaves. We do not look at physical processes. We look at an airplane. An airplane, there's a pilot, and we do not know whether the airplane chooses to fly to the right side or to the left side or to stay on a straight line. So there's ambiguity in the evolution of the object model as well. And again, we can model this type of uncertainty by an evolution model. We consider again such functions here, a probability density function which describes the knowledge that we have about the target state at a time k, a future time k, given in the past we knew that this was a state. So imprecise knowledge again, and this formula you see here is the first example of a formula that shows how pieces of imprecise information can be combined. It's a reasoning formula. We have here imprecise knowledge at this time. We have imprecise knowledge on the evolution model of the target, and this formula tells you how to get the prediction. This is the prediction. You see, it's again such a hat, and the hat has a greater width. That means the imprecision grew. As time, if we have if you have no sensor management, no sensor measurement available at this time, then in most cases you cannot do something. However, sometimes, and we will see examples of this in the course of these lectures, it is possible to exploit negative sensor evidence. Sometimes a successless attempt to see a target carries valuable information. You will see examples of this. As time goes by, you see that without sensor measurements, we have an increasing dissipation of our knowledge. Now let us assume that at this time, k plus 1, we have, oh sorry, there's some German left on the slide, sorry. At this time we have, let's assume we have a measurement. Well, a measurement is again a piece of imperfect information. Measurements are never exact, and they are not complete. We measure one aspect of the state, maybe only the position, but we're interested in the velocity and the acceleration as well, or we measure just an angle. But now this piece of imperfect information is also represented by a probability density function. In the case when we are dealing with measurements, and in the case when we wish to describe what we can learn from sensor measurements about our target state, we call such probability density function likelihood functions. Just another name, likelihood function. And this is the likelihood function of a measurement. You see the tip here. This is where the measurement is, and the width of this hat indicates the measurement error, so to say. Here we see another formula which shows us how to combine these two pieces of imperfect information. We have the imperfect information that we obtained by prediction. We have here the likelihood function, and this very important formula, it's called the Bayes formula, tells you how to combine these pieces. Actually, it's a learning formula. This formula tells you what can be learned from the sensor data with respect to the previous knowledge that you already have. And this is the result of it. So you have such a tip. So you learn something.
Excuse me.
What happened? Yeah.
I'm sorry. In the previous slide, are the two z's the same function? There's a small d and a capital D.
Pardon me? Say it again, please.
There are two z's indicating the measurement.
These are the measures. Well, I mean, we will look into this formula in greater detail. Yeah. It's just I only want to show. We will look in this in a couple of minutes. I want to show that there is a formula. This is the formula which shows you to combine these two pieces of imperfect knowledge. Yeah. You will understand that what this is actually. We will look into the notations. Just to give you the lessons you have to learn now is there is a formula that combines this type of information with this type of information. This is the likelihood function. And this is a formula which can be done by the computer, and this is the result. We will look into the meaning of the formula in a couple of minutes. Yeah? It's just to give you an overview in the beginning, so then it's easier for you to follow the mathematical details. What happens if you have more than one measurement? If you have ambiguity in this problem. For example, here, 3 measurements. If you have 3 measurements, you have more possibilities to interpret these data. There are actually 4 possibilities. The first possibility is that none of these 3 measurements is actually coming from a target, and the other 3 that assume one particular of these measurements to be true. You see immediately that in describing this situation, we need a better model of the sensor. We need to describe also the notion of a detection probability. Yeah? So the target can be missing, and we need a sensor parameter that describes this can be missing. We need also a statistical model which describes false alarm statistics. In other words, the likelihood function. So this function that helps you to learn from the data is more complicated. If you use representations of this, we will go to this future in a couple of minutes, then you end up with probability density functions which are more complex. Typically they have this multimodal behavior consisting of more modes, and these modes, these hills, reflect ambiguities that are inherent in the data. So if time goes by, we can predict them. would like to draw your attention to this small mode. So there are three modes: a big one, and a medium one, and a small one. And this is what comes out, the representation of the knowledge we have at time k plus 1. Now let's assume we have a measurement again. Let us assume this is the corresponding likelihood function. So the measurement, this that here, is at the tip, and the width is the measurement error. And this measurement, this likelihood function, obviously supports this small mode. So after applying our learning formula, we have this representation of our knowledge. You see immediately that the processing of the data in particular leads to a recalculation of the hypothesis weight. So this small mode, seen from the perspective of time k plus 1, increases in weight. Well, this leads us to the question, well, perhaps we can infer from, seen from the present, we can infer what was the past. We can infer a better knowledge from the past target state by taking the data at time k plus 1 also into account. In other words, we ask the question, how does new knowledge affect the knowledge in the past state? Yeah, what can we infer for the past? And we call this retrodiction. We have seen the notion of prediction. Prediction goes from the present to the future, and retrodiction goes from the present to the past. It improves our knowledge in the recent past. So if you apply this, we have here an example of optimal information processing at present and for the past. So that's the general idea. And before I would like to go into the mathematical details, let me show you, let me sum up first. So sum up is the lesson that we have learned. If we wish to deal with imperfect information, we have to calculate iteratively conditional probability density functions. This is the idea. Or other functions like the intensity function or the PhD or other things. We can distinguish three steps. We have the prediction step. In the prediction step, we exploit the dynamics model, employ other context information which is perhaps available, such as road maps, that we have them, and if the targets move on roads. Then we have the filtering step. In the filtering step, we exploit the sensor data and exploit context information about how the sensor works, information about the measurement error, information about the detection probability, and so on. And we have the retrodiction. The retrodiction improves our knowledge on the past. Typically, the probability density function has the character of finite mixtures. They are hilly functions with many hilltops and valleys. This hilly structure reflects the inherent ambiguity in the data. From these functions, we can derive optimal estimators, and we have to think about a proper method to initiate tracks and to terminate tracks. Here, sequential likelihood ratio testing comes into play. Before I go into the details, let me show you an example with military operational conditions. In this situation, we have in military situations, we often have problems with object detection. We have problems with the measurements, they are poor. We have problems with sensor resolution. Closely spaced targets may produce one single measurement and not two measurements. That's a typical problem with radar, for example. And the object behavior may be complicated. We can have to be aware of highly maneuvering targets that do not always maneuver. Sometimes they fly on straight lines and then they start to have a dogfight, for example. Let us show an example here with real radar data. You see now an example from a dogfighting exercise. The data have been collected from long-range radar. It was actually stationed in Canada. And what you are seeing here is the data produced by the radar accumulated over approximately 1 hour. We have here the airport, so there's an area in the vicinity of the airport is blanked. We have here also an angular sector blanked. And many forest returns close, but there's the whole area we have many forest returns. This is the scale. These are 50 kilometers. And from this airport here, 2 pairs of fighter aircraft start and perform a dogfight exercise. There are 2 pairs of aircraft, and it is clear from this figure that from this picture that it cannot be seen by the naked eye from the accumulated data. But the radar operators do not look at the accumulated data over an hour. What they see is a so-called PPI representation. So a PPI representation means we show the radar data over the past few scans, in this sense 6 scans, yeah? And so the targets appear like worms. They crawl over the screen, and the past data are just erased. And indeed, you can now see there are situations where we can't see the target. Well, the time between 2 scans is in this case long-range radar 10 seconds actually, 10 seconds. So I show now the data very fast, in a very fast movie. In reality, the radar operator would look 10 seconds, update, 10 seconds, update, and so on. So if you look at these data very fast, you have a better chance to see them. If you look them in real time, 10 seconds and 10 seconds, you would be lost. You could not understand what's actually going on. And now I would like to show you what happens if you apply this methodology, this idea with the hilly functions to such a problem. Yeah? So represent our imperfect knowledge, all these ambiguities in such functions, calculate these functions, or let the computer calculate these functions in an algorithm. And now we see these probability density functions in this representation. We depict all these hills. Now we only show you the hills, where the hills are, and where a hill is, we have a dot. Yeah, not the full function. If you have a hill, there comes a dot. In the pre-processing, we estimate the number of targets. We found out the 2 targets, a yellow one and a red one. And in the beginning, the ambiguity is very high, very large, a complicated function with very many hills and valleys. After a while, we have this representation where we can see 2 targets start. Here we have an interesting situation, a split-off situation. It's necessary in a military environment not to lose it, but it's difficult here because right after the split-off event, the orange target is passing a cluttered region. For a stupid algorithm, it's likely that the orange target is losing it. Well, so you learn with these type of methods, you can find out that there are targets at all. You find out how many, and you can follow them somehow. Yeah, you have a coarse idea. If you show this to a military user, however, he is perhaps also quite disappointed because he doesn't want to see these hypotheses and everything like that. But please keep in mind, we have another trump in our sleeve, so to say. We have this notion of retrodiction. We can recalculate our representation of the most recent past by these techniques. So now let us apply retrodiction. That means let us recalculate the hypotheses of the most recent past based on the data we have at present. Yeah. So let us look back at the track, and this is what you see. Does it run? Yes, it runs. Now the retrodiction is started, and what you are seeing now is the following. You see many of these dots that represent hills of the probability density function became blue. Blue means they could be erased. Yeah. So these hypotheses that are related to these dots had, at the time when they were formed, a significant statistical weight, maybe even a larger weight than the true hypothesis. But seen from a retrospective perspective, seen from the new data that are available, yeah, they could be erased. Yeah. At present, at the head of the track, the ambiguities are still there. Full ambiguity is at present, but it lasts only a few scans. Only some scans have to be processed to reach a fairly well interpretable trajectory of the target. So with a certain delay, you can extract the target. So at the head of the track, we have these ambiguities, but it takes only some scans to get a precise trajectory. The red and the white trajectory indicate that this is the best we can do with these retrodiction techniques. I would like to show you now what, well, also this is not a representation which is suitable for military use. I would like to show you now what could be represented to a user. We now calculate from these complicated functions only the centroid, only the expectation value, and this is just the expectation value. And see, you can see here, two targets started. We have here the split off situation. Here we have the clutter area, and sometimes it takes a while, until the track is found, So there is some delay in it until you know it, but this is not a type of radar that you use for fire control. It's a long-range radar, 50 kilometers, so you can afford to have a certain type of delay to understand the situation much better. And from such a picture, you can well understand what is going on. It's a dogfight exercise. You see how these targets maneuver. You see here in this situation, it was an ambiguous situation. It takes a while until it is clear what happened. Now, so these are real data, actually, not a simulation. This is a situation which is quite interesting. Look here, these two targets try to shoot them down, actually, and look at the white one. It takes a long time until the filter knows what happened. But then this happened. But actually, when I first produced these results, I thought myself, this is an artifact. This cannot be true. No target is flying in such a way. But then an air pilot actually told me that this is exactly what he would do in this situation. This is the situation in 3D, in 3 dimensions. In this situation, he dived down. He won another G acceleration, and he turned along his axis and tried to escape as fast as possible. So even this sharp cast can be found by these sort of things. This is the movie. I would like to stop here. You can always look up technical details in the papers I mentioned. So in these complicated data sets, with the methods you have seen, we can find things that we're not able to see from the raw data alone. This means the methods of tracking, multiple hypothesis tracking, and sensor data fusion are, so to say, a cognitive tool. A cognitive tool that helps you to improve your situation, your mental abilities, in the same way as a physical tool improves your physical abilities. Let us sum up. Bayesian sensor tracking, where we produce in the course of time, you have one or several sensors producing measurements. Each target is characterized by a state vector. The objective is to learn as much as possible about the individual target states by analyzing time series. We have the problem of imperfect information, and moreover, the target's temporal evolution is usually not well known. And the trick is interpret both measurements and target vectors as random variables and describe a probability density function, what is known about them. A solution is derive an iteration formula for calculating the PDF, develop a mechanism for initiation, exploit all background information. If you have done so, you can derive estimates along with appropriate quality measures. Very briefly, I would like to sum up key tricks of how to deal with probability density functions, just to make you a little bit familiar or to remind you. PDFs, probability density functions, are means to exploit probability statements about a random variable by integration. They are normalized and positive. There are 3 important notions. You have the notion of a conditional probability density function. A conditional probability density function describes the impact of information of another random variable that you have perhaps available, a measurement for example, on the random variable that is of direct interest for you, the state for example. So conditional PDF shows how does knowledge about Y affect your knowledge about the random variable. It is defined in this way. The marginal density is also important because it helps you to enter another random variable that is perhaps better known to you than the original random variable X. Marginalization, a very important topic. The Bayes rule, we have already seen it, how important it is. The Bayes rule is a method to calculate conditional probability density function if you have another probability density function that is perhaps better known to you. So if you are interested in this PDF and you have this PDF, well, what is before and after this given bar is swapped. If you have this, and you have also the prior, then you can calculate this probability density function. Moreover, if you have certain knowledge, precise knowledge, well enters into this formalism, you just consider probability density functions which are very, very short. And if you have a random variable x, and you're interested in a transformed random variable, which is just the transformation, then you can calculate the probability density function of y based on what you know on x. It's the so-called transfer operator. In fact, it's only one slide, and this one slide collects everything you must know about probability density functions, and this is sufficient. So it's not an easy thing. It's perhaps a little bit strange when you start working with it, but it's a finite set of rules, and you get easily familiar with them. One slide, only one slide, and this collects all you need to know about probability density functions. The Gaussian PDF is very important. The Gaussian is a bell-like function. It has the structure. It depends on two parameters. We have the center, where the center of the bell is, and we have a matrix. And this matrix describes an ellipsoid, and this ellipsoid is the shape of this bell-like structure. So a special example: the Gaussian is characterized by a vector and a matrix, and the expectation of this density is identical with the center, and the expected error of the expectation vector, which is called the covariance, just another name, is identical with the shape matrix. In practical application, Gaussian mixtures are very important, and we will see many examples of Gaussian mixtures. That means weighted sums of Gaussians. So add up Gaussians with the weighting factor, and you can model many examples of probability density functions that are relevant in practice. Now let us go back to our original question. We have a set of measurements provided by a single sensor or multiple by sensors, single sensors or many sensors, measurements related to a single or a multiple target state. Typically we write measurements as Z with the letter Z. We can write the accumulated series of all the measurements over time in such a manner. We have here the data at the present time, and here the time series up to and including time k minus 1. And based on this collected measurements, we wish to learn about the object state in the past, for the past, at present, and for the future. And the answer is given by calculating these probability density functions. So these probability density functions describe the knowledge that we wish to have about the target state at time L, given all the sensor data that are available up to and including time k. So this formula can easily be translated into natural language. This is what we want to know. And if we want to know it, we have to calculate it. If you are looking into a multiple sensor application, the same framework essentially. Here behind the given bar you have all the sensor data of all the individual sensors. However, you have to work harder. You have to look into the communication lines. You have to make sure that there's no latency, or if there is latency, you have to take into account out of sequence measurements and many other things. Also important in practice is to create a common coordinate system, which is by no means trivial. If you have two sensors, you must make sure that all these sensors can be transformed into one single coordinate system. You must register the sensor. You must make sure that the direction of north is the same for all individual sensors, and so on. But the framework is the same. Now let us look at how to calculate these PDFs. So let us assume first at the present time we wish to know the kinematic target, the state of the target at time k, given all the sensor data up to this very time. Well, we can split this time series in such a way, the present data, the past. Now we can apply Bayes' rule, this little trick we have just seen. So we swap what is before the bar and behind the bar, and we end up with this. Well, this is can be interpreted easily because we have here the prediction. What do we know about the target state at time k, given all the data up to and including time k minus 1? That's the prediction. And here we have the likelihood function. And the likelihood function describes what the current sensor data output can say about the target state, and it's called the likelihood function. So calculate the prediction and find an expression for the likelihood function, then you can calculate this quantity. Now let us look first at the prediction, how we can get the prediction. Now we wish to predict. We wish to predict from one state to the other. We wish to predict from state k minus 1 to the state k. But here we have no k in the formula. But marginalization is a trick to bring the state k minus 1 into play. So marginalization, according to this little rule, means write down the quantity that is interesting for us and integrate over this quantity, over all quantities. So we have the state k minus 1 into the play, and now we apply the notion of a conditional probability density function. We can rewrite this joint probability density function as a product of a function that describes the object evolution, and we have here the probability density function describing the knowledge of the target state at time k minus 1, given all the data at time k minus 1 at the same time. So we have here, we have closed the loop. So we have, this is the idea of an iterative calculation of this PDF. So we need an expression for this, and this is often we have an assumption that we call the Markov assumption. That means it does not depend on previous data. And sometimes you have more than one model. Sometimes our target, as in this example with the dogfighting aircraft, sometimes targets are moving without any maneuver, and then they start to maneuver like crazy. So we have to integrate more than one maneuver models, yeah? And but this is easily possible. If we have more, if we have this, then we have a larger state. We have a state that consists of the kinematic quantities, and we have another quantity that indicates in what maneuvering state the target is, yeah? And this is the same thing. We can write this as a product of two functions. We have here a matrix which describes the phase transitions from one maneuvering state to the other maneuvering state, and here we have the standard model assuming a particular model being in effect. This is so-called IMM, interacting multiple model approach. So it perfectly fits into this thing. Let us look into the likelihood function. The likelihood function describes what the sensor data can tell you about the target state. In the example single target in one clutter, the likelihood function has this expression. It's a more complicated expression than just in the case of Kalman filter. We have sensor parameters like detection probability, very important detection probability. We have the clutter density, and we have here the measurement error covariances. So if you have this model describing the target maneuver, if you have the likelihood function, these functions are depending on the sensor data that you are currently looking at. Then you have here a formula, and this is the tracking formula actually. This is the general formula that describes you how to track targets. Yeah? You have the previous knowledge, you have knowledge on how the target evolves over time. It can be more complicated, it can be an IAM model, and you have a likelihood function. It can be complicated. You get here what you're interested in. The same is true for looking at retrodiction. In retrodiction, we are interested in past target states given all the data. The same type of reasoning we have to bring, well, it's a retrodiction, we are going from the present down into the past. Yeah? So the first thing is we must bring into play the time when we're interested in at time L, we must bring into the time L plus 1. But this is possible by marginalization. Just write it down, integrate over all possible states. Marginalization, and then we apply the notion of a conditional probability density function, and we end up with this. And here we have the retrodiction at time L plus 1. What can we know about the time L plus 1, which is seen from this time in the future, given all the sensor data accumulated up to the present? So this is known. What can we do with this? This looks a little bit strange, this thing. It cannot easily be interpreted. The first thing you can say is, well, this is the target state at time L, and here we have all the measurements, up to time k, and including time k. Well, a target state in the past cannot depend on measurements you will make in future. Yeah, so you can easily drop this k and write L for this. And now we have here a situation where we have here a target state at time L, and here L plus 1. If you apply Bayes' rule, then we can swap for the given bar with what is behind the given bar. It's just a rule, and we end up with this. And this can easily be interpreted. This is the filtering at time L, what we have already calculated. This is a dynamics model, and now we just insert this into this and get the general retrodiction formula. The general retrodiction formula. It's very general. If we have Gaussians or Gaussian mixtures, yeah, then this formula can easily be exploited and leads to very fast and real-time algorithms. And if we have linear Gaussian modeling assumptions, a linear Gaussian likelihood function, a linear Gaussian dynamics model, we end up with Raufus-Priebus-Muster. Yeah? But this formula is a general one. So now I have given you an overview of the basic principles of multiple hypothesis tracking, and I also wanted to give you a flavor. This is a very powerful method, very general and powerful method. And you will see in the following lectures that PDFs are not the only way to represent uncertain knowledge. You will learn the intensity filter. I like it very much. The lecture of Royce Schrein is wonderful, and also the lecture of all the other people. They are applications of what I just presented. Tracking and management of phased array radar. I mentioned this JDL model, these different levels, and for phased array radar, for example, fighter radar here, all these levels interact. We have the lower levels, which are mostly related to signal processing, adaptive beamforming, space-time adaptive processing, detection, parameter estimation. We have the levels of tracking, of fusion of radar data with electro-optical sensors, road maps, for example, and most important, the resource management. So the process of data fusion, the process of tracking, has an impact on the process of data acquisition. In other words, the estimation theory is added by control theory, and sensor management is estimation plus control. And the full system needs to comprise both. I would like to show you this example. This is a current example that we are just preparing together with industry, a large experiment in Canada, in Goose Bay. Here we have sensors which are phased array sensors. It has to be managed. We have here a reconnaissance airborne vehicle. It produces radar plots from ground-moving targets. These radar beams have to be controlled, have to be managed. The plots have to come down to a ground station, have to be combined with electrical optical sensor by an unmanned combat vehicle to finally derive at targeting information. Just as an idea, this slide shows you, for the example of phased array radar, the information flow for sensor management in a way is applicable to other applications as well. So we have a tracking system here, and this tracking system has this triggers and starts the use of the sensor. You have the tracks are there, and as soon as the track becomes bad, yeah, as soon as there is a lack of information, the tracking system starts either a track update request or a track search request. These requests are collected here by the priority manager. Priority does the charge assessment, overload handling, graceful degradation, and if there is a request which is important enough, then we use it for the update settings. We prepare the sensor for update and search. We send out information to the antenna. The antenna sends out energy into the observation space. We receive the echo. And if we found the target, actually, that's fine. If we did not find the target because it has strongly maneuvered, we have to start local search. We will look into local search. And if we have here in the search request an initial detection, we have to confirm this. If we finally have the measurement, we do the signal processing. We derive angle measurements, range rate measurements, range measurements, and so on. And this goes to the tracking system. The tracking system processes the data, prediction, retrodiction, filtering. We have seen this, calculates the next update time, and the loop is closed. So let us sum up. The sensor resources are allocated by the tracker. The tracker has to calculate adaptively the next revisit time, depending on the lack of information he has. We have to select the next beam positioning, and if necessary, we have to do local search. We can do this, and we can only do this if we formulate a model, and this model has to be incorporated into the tracking algorithms. And for a phased array radar, for a pencil beam radar, this is a good model. We have here the definition of the beam positioning error. Well, we only get a measurement if the beam points towards the direction where the target actually is. Yeah, so that's quite clear. And so the beam positioning error is part of the signal-to-noise ratio. Now we have here the situation that the signal-to-noise ratio depends on both the target position, the target state actually, and the position, the direction of the beam, where the beam points. And you see here in this simple model, we have here a constant and here an exponential, and here is the beam positioning error. As soon as the beam points to a different direction as where the target is, we have here a very large quantity. This error is large. Exponential minus a large quantity is 0. That means that the signal-to-noise ratio is 0. We cannot see the target. And very important, there is a link between the signal-to-noise ratio, the basic radar quantity, and the detection probability. We need the detection probability in our tracking algorithm. Yeah? We have seen the detection probability is an important quantity in the likelihood function. And here, by such formula, this is a swirling one formula, there are other formulas, just an example, we see how the signal-to-noise ratio is linked via a detector property with the detection probability. And the detection probability is the quantity that we need for tracking. And the PD, the detection probability, can be a function of the state, of the target state, of the unknown target state that has to be estimated. Now let us look at beam positioning and local search. Well, the first dwell is quite easy. What to do? We point the radar beam towards the predicted target position. If we receive successfully a detection, we do the filtering and the prediction, we calculate the next revisit time, and the locus closed. Yeah? What happens if we have no success? If there's no success, the target has started a very strong maneuver, and we did not actually detect the target. With the phased array radar, where we have to control the beam, well, like a pocket lamp in a dark room, it's very necessary to find the target again. Well, if we have no success, we still have a negative sensor output. We know that we have looked into this direction and did not receive the measurement. This is information. It's not a sensor measurement, but it is a sensor output. I've looked into this direction, I've not seen the target. Yeah? That's information, negative sensor information, if you wish. And let us call this negative information not D the first time, not detected the first time. So this negative sensor information is behind the given bar. It's part of the information that we have. And if we apply now the Bayes rule, this nice little formula, we can calculate this according to Bayes rule. We bring this before the given bar, bring this behind. And then the first factor here is appears the probability of having not detected the target. And this is 1 minus the detection probability. Yeah? So the processing of this negative information leads to this expression 1 minus PD. Yeah? And this PD depends on the target state. So we have here a function of the target state that looks like, in a way, as a likelihood function, and modifies and corrects this probability density function that has no knowledge of this negative sensor output. That means we can learn something from a negative sensor output. So the management strategy would be, well, calculate this, and then point the beam to the maximum of this conditional PDF. This is the rules. There are other rules. This is one rule. If we have a successful detection, we do the filtering, do the prediction, calculate the next revisit time, and go back 1. If this is not, if we have no success, we calculate the PDF with 2 pieces of imperfect information. I would like to show this in an example. You see here the PDF of the target direction. Yeah, we have here the direction angle, in direction cosines in both directions, and we have here the PDF. Here it is light. We have a high probability that the target is here, and here it is small. The target position is here, the target has to start a strong maneuver. Yeah? If you point the radar beam towards this direction, which is reasonable, which is the sinusoid, we receive a detection probability for this target position of only 26%, not high. Let us assume that we did not succeed in detecting the target. So we point the beam into this direction, and now we calculate the PDF given this negative sensor output. Then we obtain this. Yeah? So this is the result after processing. Well, I tried to look into this direction and I did not succeed in detecting the target. So this area increased in weight, and this became smaller and moved a bit. Here, the maximum leads to a much higher PD. Yeah, 50%. Could increase the PD by a factor 2. Let us assume, again, no success. 2 pieces of negative information. That's the resulting density. Yeah? So the filter tries, well, perhaps I try again, first try. Well, perhaps I have not just seen it. Yeah? And then we obtain this density. 3 pieces of negative information, and now we see we have 2 local maxima. Yeah? We decide, well, this or this, let us look at this direction, but then we have accumulated much probability mass around the 2 target positions. Yeah? Only by processing a negative sensor output. Yeah? It's a local search strategy. And search is very important. Yeah? So the Bayesian formalism allows you also to search for targets. Yeah? By exploiting sensor output. So we process the data in advance. So let's summarize. A negative sensor output, that means we're missing, but it's expected data provides information on the target position. It has direct impact on the sensor management. The prerequisite is an appropriate sensor model. Let me skip that. We have no time. I have to skip that already. Also, sorry. I wanted to comment on this. An important application is ground picture production. A modern, challenging application for target tracking is the production of ground pictures, specifically done by a sensor type called GMTI, Ground Moving Target Indicator. It is just important to produce a ground picture. Ground surveillance is difficult. We have to use airborne platforms because we couldn't see ground-moving vehicles because the radar horizon is so small. Typically airborne platforms. We wish to look at vehicles, at ships, low flyers, other UAVs, for example, or helicopters, radars, convoys. We have to take into account occlusions, Doppler blindness, and topography. We look into Doppler blindness. We can exploit roadmaps and train information, tactical rules. This information we have in ground surveillance, not so much in air surveillance. And we have dense target, dense cluster situations, and highly ambiguous situations, a situation where multiple hypothesis tracking is very important, very, very important. Now, I would like to show you some screenshots. These are screenshots from the German ground surveillance, the ground exploitation station where we implement our algorithms. Without any tracking algorithms, you see clouds of highly fluctuating clouds of sensor measurements that do not tell you much. The operator wants to interpret them in such a way that he is clear that these are ships and that there is something moving on the airfield, and some airplanes are taxiing, some are starting, that there's road traffic. And here in this situation, very quickly a helicopter passed the scheme. And this was important, actually, in this situation. So with the naked eye, the operator has hardly a chance to see when such a helicopter is crossing the scene. You need cognitive tools. You need all the algorithms we have talked about already. All these activities are embedded in a large NATO program, the so-called MAGIC program, multiple sensor, aerospace to ground joint interoperable ISR coalition, but it's a sort of AVAX for ground surveillance. There are several platforms, different platforms. They provide measurements. These measurements are distributed among the coalition of participating nations. Important role play the so-called CDS, the coalition shared databases, and each nation has its own interoperable ground exploitation data. Ground exploitation station, and in this station the algorithms are running, and the algorithms we are talking about in this lecture series. This is an example, screenshots from magic examples, ground moving activities. We wish to track them. We wish to have an automated track before detect, to find them. We wish to maintain them, even in case of clutter. We wish to estimate the target number. We wish to exploit roadmap data. If roadmap data are available, we can fastly extract tracks. We can produce precision tracks. We can produce tracks that are continuous, and we can even classify off-road and on-road targets. If a road-moving target is leaving a road, that's quite interesting. So let us look, why is GMTI fusion difficult, and why does it need sophisticated algorithms? I would like to illustrate this by an example. A movie tells more than 1,000 words. I'm sorry. And this little movie is just an illustration. It's a simulated example. It shows two types of sensor platforms. We have a standoff platform, perhaps similar. Perhaps could have in mind the American Joint Stars platform. We have here a platform which is typical. Sorry. Do you hear me? Yes. We have here. Oh, I must stop here because I want to explain something. We have here the following situation: a standoff platform. No, thank you. Do you hear me? Is the micro okay? Do you hear me in the other room? I interpret this as a yes. We have the two platforms, and here I showed you the detection probabilities of these two platforms. The orange, so detection probability as a function of time, and orange for the orange platform, and red for the red platform. This is the target that moves here on the ground. And in the beginning, the detection probability is high, yeah, quite good. We can track the target, but after a while, the detection probability drops down. It drops down, goes down to 0, remains 0 for a very long time. Yeah, this is deadly for trackers for more minutes, and then it comes back again. The same happens for the red target. And here you see that the road-moving target is leaving the field of view of the sensor, and then again the PD drops down and is 0 again for a very long time. 0, 0, 0 for many minutes, deadly for any tracker. And now it comes back again. In the meantime, nothing serious happened actually. We had here the target. The target moved on the road. It did not move on the road, and we have these platforms flying on a straight line. Why is this so strange? Why is this so strange? Well, the reason is, well, if you look with our radar to the ground is a big mirror. If we send out a radar beam to the ground reflects it. And now the task of space-time adaptive processing is to find in this very big echo those echoes that have a different Doppler frequency than the surrounding ground. The ground, if the platform is moving, the ground has a relative speed, so the echo from the ground has a Doppler frequency, and it's Doppler shifted. And those targets that are moving relatively to the ground have a different Doppler frequency. And this can be exploited, the Doppler effect can be exploited by signal processing people. And this helps the signal processing people to subtract the ground clatter and to find only the ground moving target. This is the reason why GMTI is called GMTI, ground moving target indicator. You find those targets that have a radial velocity that is different from the radial velocity of the ground. And this is what I've shown here. Here I've shown as a function of the time the radial velocities. You see here the solid line. The yellow solid line is the radial velocity of this ground-moving vehicle over time, and the dotted line is the radial velocity of the surrounding ground patch. Yeah, and you see here that here, because of the sensor-to-target geometry, is so that both lines intersect, and here both radial velocities are identical. This means the target cannot be seen. Tagging probability is 0. For the radar, this ground moving target is identical to a ground clutter, pressed. Yeah? And typically, these curves have sliding intersections. Yeah? If they intersect, yeah, they remain close for a very long time. And this is the reason why we have here a long period of Doppler blindness. That's typical and general property of GMGI sensors. And here, the target has stopped. This can happen. Target stopped. A missile launcher, for example, that is on the way, is not dangerous. As soon as the missile launcher stops, yeah, it cannot be seen, because in this case, the radial velocity is identical with the radial velocity of the ground. Yeah, so it's a ground moving target indicator. The good thing is that this property can be brought into the tracking algorithm. I said already, the signal-to-noise ratio is the relevant quantity. And here we have all what is relevant to radar, and here we add another factor, and this factor describes this phenomenon of Doppler blindness. Yeah? Here we have 1 minus an exponential, and here we have the difference between the two radial velocities. And if these radial velocities are close to 0, we have exponential up to minus 0, which is 1. 1 minus 1 is 0. The signal-to-noise ratio is 0. Yeah. With this little formula we have already seen, we can transform this knowledge into the PD. If we have it as a detection probability, we can enter it into our tracking algorithm. The nice thing is that the corresponding likelihood functions that reflect this property, that take into account the property of Doppler blindness, have now a special structure. They are more complicated, but they have the structure of a Gaussian sum. It's a constant plus Gaussian, the sum of Gaussians, which are properly calculated. With sums of Gaussians, you can easily handle the Bayesian formalism and essentially exploit the state dependency of the detection probability. I would like, I have to skip because I have not much time. I would like to illustrate this, but before I can show another movie, a last movie, I would like to give you an idea of roadmap-assisted vehicle tracking. Typically, in ground surveillance, if there are roads, targets move on road mode. So you have to bring the road maps into the tracking algorithm. That's context information, background information that must be used. Typically, a road is represented by such a graph. You have the nodes, the sources, crossings, traffic signs, and traffic sign. A street changes its character. For example, such signs can indicate a bridge. And then we have the edges that represent road segments. And these road segments can be approximately given by polygons to be taken from digital road maps, along with mapping and discretization errors. In road coordinates, the vehicle kinematics is easy. It can be described by the arc length of the corresponding road segment and the temporal derivative. So what you count on your kilometer counter in the car and what the speedometer shows. So an easy state, two-dimensional state. The prediction in road coordinates is easily done. It's just a predicted update step. However, if you wish to process sensor data, you have to process them in sensor coordinates. Yeah? So we have to represent our knowledge in sensor-related coordinates. So here is the knowledge represented in road coordinates with reference to roads, and here we must represent the same type of knowledge in sensor coordinates. Yeah? And in sensor coordinates we can process the data. Now the trick is to create this transformation. We have a representation of our knowledge in road coordinates. We exploit the road map and exploit the corresponding mapping errors to calculate the probability density function in sensor coordinates. The same information in a different coordinate system. This can be done actually, and this mild approximation, actually this PDF, this representation has the structure of a Gaussian sum, which makes it very convenient in algorithms and makes it accessible to real-time algorithms. I would like to close this lecture with a little movie which illustrates everything that we have learned so far. In this little movie, you see a road network, and in the first stage you see the measurements of the ground moving target indicator radar. So the measurements in the beginning. Here we have a occlusion, a terrain occlusion. We cannot see the target, so therefore we have no measurements. Here the target stops, and therefore we have no measurements. Yeah. Then the target moves again. Here we have a situation where, well, it's a low Doppler region. Yeah, we have only a few measurements. Here we have an intersection in a train obscuration, and right after the train obscuration, we have a Doppler obscuration, technical obscuration, train obscuration. Now let us show what a tracking filter does, which only has the sensor data, which does not have context information on the road, context information on the train obscuration, and no context information on the Doppler notch, on the Doppler line. This is what the filter does. But at the beginning it's quite okay. It has an acceptable track, not very precise, but it's okay. Then we have this train obscuration, no measurement occurs. The tracker has to predict and loses the track actually. We have to restart the track loss, track fragmentation, which is bad. Again, target stops. Again, we lose the track fragmentation. Then here we have large errors. In this situation, the tracker does something very stupid. It predicts where the target is definitely not in between these roads, and we again have track loss. Well, track accuracy is good, but track continuity is even better. You need long continuous tracks because these tracks are the backbones of your situation picture. On these tracks you accumulate the classification information, the identification information. If your track is lost, all this information is also lost. You need continuous tracks. Yeah? So this is very bad. And now I show you the situation when you have a context-based tracker, which is context-based tracker. But in the beginning you see that exploiting roadmap information helps you to create precision tracks, which are perhaps interesting for targeting. And in this situation, we do not lose the track. Why? Well, we know that in this area the detection probability is 0. We know this, and the filter knows it. Yeah, and this means that if the target is entering this area, then the detection probability density function will decay. But as long as we have no measurements outside, the filter knows it must be inside. Yeah, so the filter knows and sits like the cat before the mouse hole. And as soon as the target leaves the occlusion, it has it again. It is easy in a single target situation, but even in a multiple target situation, you can do a sort of bookkeeping. Yeah, the filter knows it must be there. It's not stupid; it just loses the track. In this situation, the filter target stops. The sensor does not produce measurements, and still a context-based tracker is able to identify this must be a stop event. Why? Why is this possible? Well, if there are no measurements anymore, then the filter has to predict. However, the filter knows how this Doppler processing works and knows if there is no measurement, then probably the radial velocity of my target is too close to the radial velocity of the clutter spot. And this negative information is as valuable as an additional component of a measurement. Yeah? The same way as we have seen this in the local search. So this negative information, this better model has a consequence that the PDFs dissipate only along a certain dimension. The PDFs remain stable along another dimension. Yeah, we have additional information, and we have road information. The road information says the PDFs can only dissipate along the road. And now, if we do the fusion, if we bring both into intersection, yeah, then we can indicate the target has stopped. And this stops my presentation.
I didn't mean that. Thank you.
That's a smoothie run after that started. Are there any questions?
Can I just suggest you take questions over lunch? Because
Yeah.
we're already running late.
Yeah.